Welcome to your next video on matrix inverses and matrix equations. You'll notice that the first thing that we're going to discuss is something called an identity matrix. All right? Think about when you hear the word identity, what does that mean to you? It hopefully means it's the same, it's you, it's something that isn't going to change, it's your identity. Well, the actual definition for an identity matrix is a square matrix, which that is the important first start, is that it's a square matrix, a 2 by 2, a 3 by 3, a 4 by 4, with ones along the diagonal, and all others are actual zeros. So you'll notice the two square matrices that I have is an I2 matrix, or that means it's a 2 by 2, or an I3 matrix, which means it's a 3 by 3. Now, one thing is these are not augmented matrices. Okay? That's an important piece of information. So we don't know what like each of the A, or in this case, X's either or Y's are equal to, but we really use these to multiply or add things to these matrices. So a square matrix has ones along the diagonals and zeros all over. And you may say, okay, well, why is this important? If we have in this case, a 2 by 2 square matrix with the first one, and we multiply it by something else. In the past, we had to do our row by column multiplication. So we had our 2 by 2. The next matrix that we have is a 2 by 3. Notice how our 2's are the exact same in the middle, which is what we're looking for in order to be able to multiply. And the end result is a 2 by 3, a 2 rows, 3 columns. So we know our final answer would look something like that. And if we would actually go through and perform our multiplication, we would have our first row multiplied by our first column. So we would do 1 times 4, which is 4, 0 times -7, 0. Add those two together, and we wind up with a 4 for our first answer. We keep going, and now if we do row 1 times the next spot, our column 2, 1 times -2 is -2, 0 times 5 is 0. We end up with a -2 in that case. Notice that since we're multiplying the second matrix by an identity matrix, so far the resulting matrix is the exact same. So 1 times 1 is 1, and then our zeros are obviously going to cancel out to be nothing else. So what that is telling us, and we can continue to do this for each one, but that means we should get the exact same result that we had as we started with, because we're multiplying by an identity matrix. The reason that this is kind of helpful and important is because of something called inverses. You have background knowledge on inverses. You have some, hopefully, memories about inverses and switching x's and y's and ordered pairs switching and domain and ranges switching, because those are related to x and y's, and even your asymptotes switching as well. But your goal is to try to solve for this inverse. Remember, we do that by actually switching the x's and y's and then solving for your new y. So we would subtract 6 from this case. X minus 6 is equal to a 3y. We divide everything in here by 3, so that we wind up with a y that would have to be equal to a 1/3 x minus 2. That means the equation that we found and the original equations are actually inverses of one another. They have a lot of very opposite properties to one another. Matrices have inverses as well. Well, some of them have inverses. So it says only square matrices can have an inverse. So that's the first important piece of information. Only square matrices actually have our inverse, but not all square matrices can. So if you're given a 2 by 3, you know right away that does not have an inverse. You don't even need to do anything else. But if you have a 3 by 3, then you will have to do some checking to actually see if the inverse works. Right? So now you might say, well, how do we have to solve this? A little bit of notation here for you. It says if a matrix has an inverse, then you can take this A, and again, this is just the original matrix. And I don't want the notation to get in your way. It's just the original matrix. And if you multiply it by the matrix inverse, you should be able to get an I or an identity matrix. So you multiply the original times its inverse, and you get an identity matrix, which actually works out really nice because now what we are going to do is kind of switch that property up a little bit to actually find some inverses here. Right? Notation on the right is just the exact same thing, and it will still equal, if we switch the order of them, it should still equal your identity matrix. So the first thing that we have to do here is determine if these two are inverses of one another. So we have to actually use our multiplication, or we can actually cheat a little bit, and we can put this into our calculator to see if this equals an identity matrix. So let's try that. If you don't have your calculators handy, please feel free to get that out, because now we have to put this first matrix into our calculator. So we're going to go into the second, we're going to go into the matrix, and I'm going to go over to the edit, because I need to edit a matrix, and now I'm going to type in here a 3 by 3 matrix. 3, go over here, a 3 by 3, and now notice how my matrix actually got smaller, like it should have. And I'm going to plug each number in here. I'm going to plug in the very first one. I have a -1, then I go over and plug each one of these in, and now so you can do the same thing on your calculator so you know the keystrokes that it takes. And I'm on my last row now, -1, 1, and then -1 in this case. So again, once you have each one of these, I would strongly recommend double checking to make sure you put the numbers in correctly, and you can go second mode or second quit in that case. We need to now put the other matrix actually in here as well. So you go back into the matrix, but now when you go to the edit, you don't want to put it back into the A spot, well, because you already have that matrix in there. We want to go down to the next spot, and you can plug it into the B spot. Now we need this matrix also to be a 3 by 3 matrix. And now the matrix is adjusted to be a little bigger, and let's put each one of these numbers in now. 1, 1, 1. Keep going again. Make sure you are double checking your signs. Make sure you are checking the numbers in the right spots. It's very easy to miss a spot here or miss a number as you're plugging them in. All right. Now we can second quit again. Our goal is to multiply these two things together. So yes, in our calculator will be able to multiply matrices together. So we go back into our matrix. Notice how A is the first one that we put in, and that's listed first. So we press enter there. Now we multiply in between. Okay, push the multiplication symbol, go back into your matrix, scroll down to the B, and put that in there. And now your calculator has the A matrix times the B matrix. We enter those out and look at what the result is. The result is a square matrix, which means these two are inverses of one another because their answer actually led to a square matrix. So we could go back here to our actual notes, and again, we still have to show what we got as a result in our calculators. And again, no augmented matrix here, just all ones and zeros. So our final answer would be yes, they are inverses. And our square matrix confirms, and yes, that is the work that we would have to show in order to say that these are inverses of one another. Okay? So that's one way to confirm or prove if two matrices are inverses of one another. But now we can actually calculate how to find this. All right? And here's the rule of thumb. An inverse for a 2 by 2 matrix has a little equation to it. And this, on a test, you will not be able to use your calculator for. So this is all non-calculator. And when I say non-calculator, I just mean that you can't use the matrix function of your calculator. Right? You can still use your calculator to abstract, multiply, and divide if you want to check answers over, but you should not be using the actual matrix part of this. That is an important piece of information, especially when you come to the test. Right? And I have a sample matrix here, a 2 by 2 matrix. Notice how I have an A, a B, a C, and a D. Those just stand for any numbers that could be in those spots. And in order to find what the matrix of this is, there's a little pattern here. The first thing that we have to do here is to take 1 over, and then we have to multiply AB minus BC. So that will eventually be turning into a fraction that then we are going to scalar multiply by this jumbled order. And notice how the A and the D switched in terms of the matrix. The B and the C switched as well. So calculating this by hand takes a little bit of work and a little bit of practice. So let's actually do this with an example. So the step number one, given this matrix, is to figure out what the AD minus BC is actually equal to. So we take the matrix that we have, and notice how the A and the D are the first and the last numbers, the spot 1, 1, and the spot 2, 2, the diagonals. So we have a 1 times 5 minus, and I'll put in parentheses here, my B times C, my 2 times 3. So I end up in this case with a 5 minus a 6, or I end up with a negative 1. Now be careful, because that means we have a 1 divided by a negative 1, since our first step actually is a fraction. Now, the nice part is this fraction turns into just the whole number. So really, we just have a negative 1 that we got from this answer. So that is our step number 1. Our step number 2, though, can actually go through, and now we have to multiply this negative 1 with our matrix that we have. And notice the matrix needs to change order of the numbers that we have. So what was our D value in this case now is going to be, when we rewrite it, in that very first spot, which means for us, we're going to have a 5 in that case. Right? We can go through now and say, well, the A that we had is actually going to be the last number. So that means our 1 is going to be the last number. And the only difference, and this is kind of nice, that happens with the B or the C value that we have is that they turn negative. So the 2 is going to stay in the exact same spot, except it's negative. The 3 is going to stay in the exact same spot, except it's going to be negative. And now all we have to do is actually scalar multiply that negative 1 into our matrix. So when we multiply the negative 1 in, well, it looks pretty nice. Our inverse of that case is going to be a negative 5, is going to be a 2, is going to be a 3, and is going to be a negative 1. So what we just did was we found what the inverse actually was. So this is the inverse of A, or if we want to use more appropriate terminology, A to the negative first. So now we could double check this in our calculators if we wanted, but we could be able to take the A matrix that we had, the 1, 2, 3, 5, multiply it by the new matrix that we got, negative 5, 2, 3, and negative 1, and we should be able to get an identity matrix from that. So I do have one more example here, because this can kind of show up a little bit differently depending on your scenario. Because what you have is still the exact same first step, where you have your AD minus your BC. And as you're going through, well, let's try that. We have our 4 times negative 3, and then minus, and now inside we have a 6 times 2. When we do this, we end up with a negative 12 minus 12 in this case, and be very careful as you look through here, because I actually want to change one of these numbers just a little bit, and I want to make that into a positive 3. My bad, my apologies there. Because if I do that, and I change my multiplication just a little bit, I have my 4 times 3 that's inside this first one. I have a 12 minus a 12, or in this case, I wind up with a 0. We know that if we tried to put a 1 over 0 in front of any matrix, well, our calculator's not going to like that very much. So this would be an example of a 2 by 2 matrix that doesn't have an inverse, which can happen. All right, there's no necessarily rhyme or reason. You can't tell just by looking at it. But when you do that AD minus BC, if you get the AD basically to be equal to the BC, then you know you're going to get something that doesn't work out. Right? If you would like to stop the video at this point to do the practice that's associated with the 2 by 2 matrices, you most certainly can do that, because I am going to move on and show you how to work with solving the 3 by 3 matrices with this method. So now, the next step that we have here is going to be how to actually write a matrix from an equation and then hopefully help solve it based on inverses. So if you notice some information here, All right, we're going to have a little equation that we're going to start to solve, and it's actually a coefficient matrix that we're going to multiply with a variable matrix that's going to be equal to a constant matrix. And you may say, well, what in the world is that? All right, I just have two different system of equations here. All right, x's, y's, the second one that has x's, y's, and z's. So the key here is that we are having these in the correct order with our x's first, our y's next, our numbers afterwards. So I do need to change this first one just a little bit so that we have an equal 3 at the end, and then I have my x minus y that equals a 5 as the next part. So what our goal is to now write this in the form that is listed above with a coefficient matrix. So now in that case, I'm going to separate that a little bit, and I'm going to write just a coefficient matrix with the x's and y's. So kind of like before, we know that in this case, we have a 2 that is listed with that x. And then the very next thing that we have is going to be the y. It's the first coefficients that you actually own. The next spot is going to be the coefficients of your second equation. Very similar to what we have. But what we're going to do now is we're going to identify that these are x's and y's. So if we were to multiply, we would say that 2 has to be multiplied with the x, because that's our row by column multiplication. Our 1 has to be multiplied with the y. Okay? And our variable matrix, literally it's just that. It has variables only in it. And now, after the equal sign, is when we have our constant matrix. So we are looking now at the parts that we actually have after the equal sign, which is just our 3 and our 5. So this is going to be the first step when we actually start to solve here in a second, but it's going to be to make sure that we can write this, what is actually called matrix algebra equation, right? So now if we're looking at the next one, again, you have to be very careful that you keep all of your variables in the same line, in the same order. So we need to make sure that we rewrite this so that our x's, y's, z's are all in that order. So for that first equation, kind of tricky because you have an x that needs to be first, and that x actually is negative. You have your plus z that is equal to a 7. The second equation is kind of already written nicely for you, so you're all good with that. And last but not least, notice how you have a 0x in that case, minus a y, plus a z, that's equal to a negative 1. And now as we go through, we can write our coefficient matrix, the matrix with just the coefficients for our variables. So the key here now, the big difference, is that you have 3 variables, which means you are going to have an x, a y, and a z, which also means you should have 3 total equations, 3 total rows in your matrix. So we have a negative 1, 1, 1. You have a 1, negative 1, negative 1. And you have that 0, negative 1, and 1. And after the equal sign now, we have our 7, our 2, and our negative 1. So we have now identified what the matrix equations would be for both a 2 by 2 and a 3 by 3, which is going to lead us into the next step where we can actually use our calculators. Here's going to be some awesome part. Okay, so we have found one method that we can use in order to try to solve a 3 by 3 matrix. Okay, and if you remember, it was reduced row echelon form. It was REF. All right, there's another way that we can use this as well. Okay, and it's to solve a square matrix. So the key here is that the equation that I have here, and there's a lot of information. I kind of want to just give you a quick background as to why this happens. All right, if we have A, which is our coefficient matrix, and we have an x in this case, that is our variables, our variable matrix, that equals to our B in this case. We can go through and we can figure out that in order to solve for x, we can take the inverse of the very first one. So our goal now is actually going to be to have the inverse of A multiplied by the constant matrix. And this is going to help us solve for our actual variable that we're trying to find. So you're going to see me write the negative, or A to the negative first, our inverse, multiplied by our B is going to be equal to our x, right? And we could go through and we could actually show matrices in order to see why and how this actually happens. So let's actually give you an example, all right? when you have a 3 by 3 matrix, you will always be able to use your calculator. All right? I will never make you do by hand the things that you were doing for the 2 by 2 matrix. So 2 by 2, pretty much always by hand. It's kind of a good way to think about it. As soon as you have a 3 by 3, that's when you're going to show me in your calculator some of the things that you actually put in here. So for this first equation, notice how, again, we have some things that work out nice, some things maybe aren't, written the way that we think it should be. One thing to kind of note here, looks like there should be an equal sign. That's actually before that 6. Just kind of keep that in mind as we're solving this problem. Because now the first thing we have to do is make sure our order pairs or that our matrices, our equations here are in the correct order. So I always like to just make sure that if I don't have a y, I always want to put it in there so that when I rewrite it, we find it. In the second equation, it looks like every variable is already here, so we should be okay. And then last but not least, I have an x minus a y plus a 0 z. In that case, that should be equal to my 6. And now I can actually set up, in this case, each of my variables. Okay, I have those. I can make my matrices. So, here we go. Let's put it in the same form that we started here. We have our coefficients. A 1, a 0, and a 2. A -1, a 2, and a 3. A 1, a -1, and a 0. So we start out by writing our, and again, if you want to put the note down, these are our coefficients. Our next part, it may not seem like an important piece, but it's going to help us when we actually put some of these things into our calculator. We have our x, y, and z. These are our variables and what they're actually equal to in this case. And at the end, we have our constants, the numbers that are after the equal sign. So in this case, it's a 6, a -5, and a 6. And now our goal, we know that in this case, your second step is going to really lead you into your inverse of your A being multiplied by your B is going to be equal to your x, y, z. So if we're thinking about this, this is really our A multiplied by the x that's equal to B that we had at the last step. So the first thing that we need to do is to find the inverse of this 3 by 3 or to find the inverse of our A. The good news is, don't do my hand. Your calculator will give you that option. So now let's look at our calculator and let's actually put this matrix in. So now we're going to have to go to our matrix, okay, go to the edit because we want to actually change one. And this is where you can make a decision. If you want to keep the other matrices in your calculator, if you have them in, you can do so. Or if you want to get rid of them, switch them, right over them, you can do that. Right? I'm going to go back into my A. It's easier if I keep the same letters as I'm working on right now. And I know that I have a 3 by 3 matrix that I need to have, and I need to put my numbers in. Okay, so I'm putting the 1, the 0, the 2 in. I'm putting the -1, the 2, the 3 in. I'm putting the 1, the -1, and the 0 in. So I have what my A matrix actually is. I'm going to double check to make sure all my numbers are correct, and it looks like they are. I second and I quit that. What I can do now is I can get that to show back up in my home screen. I go back to my matrix. The very first one has my new A in there, and I'm going to click that A, and we actually have an inverse button on our calculators. You'll notice that actually where I usually push the matrix button, the blue part, if you look at the black part, it says X the negative first. Without clicking blue, just click that button. It automatically will do the inverse for you. And if you press enter now, it tells you what the inverse of this matrix actually is. So now the key is we can write this down because it's a little bit of a hint. We know that our A inverse is a 3, a -2, and a -4. It is a 3, a -2, and a -5. And a -1, 1, and a 2. So this now is our inverse of A. We know that we can multiply that by our B inverse. So our B inverse in this case is our 6, -5, and 6. And now our goal here is to actually put this into our calculator and be able to multiply this together. So we need to actually put the B matrix into our calculator. So let's go back to the calculator. Let's go back to the matrix that we have and over to the edit. Go down to the B spot. Now this matrix has 3 rows, so I agree with the 3 part, but only has 1 column now. So notice in this case we have to put our 6, our -5, and our 6. And now we clear out of that. And this is where your keystrokes are very important, because notice how the last thing I have in my calculator is my inverse of A. Just like if it was a number, I can just click my multiplication symbol, and it's going to bring down the last thing that I have. And now what do I need to multiply that by? I need to multiply it by my actual B matrix. So I don't need to go into edit because I'm not trying to change it. I just go down to the B, I click enter, and now it's saying, all right, I'm going to multiply that inverse that you had by B, and it's going to solve for what X, Y, and Z actually are. So without using any real algebra whatsoever, no solving like you had to do with a 3x3 matrix and doing all that work to solve for X, Y, Z, your calculator automatically did that for you now. And you were able to find out now that your X was equal to 4, your Y was equal to -2, and your Z was equal to 1. So now the work that I'm expecting you to show is this step number 1. Right, is for sure the matrix that you found and actually multiplied together from the inverse, and then your final answer. So those same 3 steps as you're going through. Right? We're not going to finish the rest of the notes that you may have if you did print them out, but you can now end the video and start on the practice of 3x3 matrices.